Hi everyone, this is Dr. Chin, and this is a brief lecture covering a portion of Chapter 8, Cognition and Intelligence. So in the first half, basically in today's online lecture, we will be talking about how we think. That is basically the processes that are involved in resolving, challenging cognitive efforts. The second half, that pertains more to intelligence, refers to, studying how well people think. And so, on a general level, that helps me to conceptualize or to compartmentalize the various topics that we'll be covering in this chapter. The first half, which is mostly what we'll be covering today, covers cognition, so basically how we think. And the second part covers intelligence, studying how well people think. So, as said before, right now we are going to cover the cognition piece right here. That is, we're going to take a closer look at how we think and factors that influences our thinking abilities. And this can be further subdivided into problem solving and decision making. So let's talk about problem solving first. And this next slide over here is going to cover the second part of the chapter that discusses the study of how well we think. And the study of intelligence is cognitive intelligence is one of the main things that we'll be discussing in this particular chapter. We're not going to talk about this topic in today's lecture just because of time constraints, but we will be covering this at our regular face-to-face class that is coming up. So to get your brain juices flowing about problem solving, I thought it might be fun to start off with a riddle. This is called the Mysterious Umbrella Elevator Story. So if you've done this before, then you probably already know what the answer is to this riddle. If you have not, click on the link that is in the PowerPoint slide, or either that, or you could just watch what I'm about to stream on my screen right now. It's going to present to you a particular situation and then ask you basically why a person has to do a particular type of action to get to a goal. And then after we resolve the riddle, I want you to think about what assumptions you would need to break in order to solve the riddle. Like I said, you can watch this by clicking on the link that is in your PowerPoint slides, or you could just, if it's clear enough for you, just watch this in this video that I'm about to stream on my computer. All right, so why does he do that? Why does he only go all the way up to the fifth floor when he is traveling from bottom to up? But on rainy days, why does he go all the way to the top? So you might want to, pause this online lecture to think about this, see if you can figure this out. But if not, I'm just gonna go ahead and let you know the answer just by playing the rest of this video. So does that make sense? So because he's pretty much not really tall. His hands cannot reach the buttons on the very top, but on rainy days, he has an umbrella, and he uses that umbrella to press the buttons at the very top. So there are a couple of assumptions that you need to break in order to solve this riddle. For number one, you can't assume that everyone who gets on an elevator is of the same height, and that is what most people probably assume or think about when you think about people going onto an elevator. The other thing is we also cannot assume that people use umbrellas only for keeping themselves dry. People can use umbrellas for other things that may not be what the umbrella was originally designed for. Being able to not assume that people use umbrellas only illustrates how it might be important to get over our functional fixedness, which we'll talk about that in a couple of slides from now, which is basically one of the barriers to problem solving. And when we assume that everyone is of the same height, we're basically imposing unnecessary constraints onto the problem itself, which is another barrier to problem solving. So we'll talk about those two barriers in just a little bit, but I thought this might be a useful and fun exercise for us to think about. When it comes to solving difficult problems, what are the common barriers that tend to get in the way of effective problem solving? All right, so let's first talk about the types of problems that we typically face in our everyday lives. There are essentially three types of problems. So most of everything can be categorized into one of these three categories. The first type of problem is problems of inducing structure. This is where people are required to discover the relationships among numbers, words, symbols, or ideas. The next slide talks a little bit more about this. Right now I'm just going to very quickly go through the definitions. Problems of arrangement refer to when people have to arrange parts of a problem in a way that satisfies some criterion. These types of problems, the problems of arrangement, are often solved by insight, which is a sudden discovery of the correct solution following incorrect attempts based on primarily trial and error. Lastly, problems of transformation. Problems of transformation involves carrying out a sequence of steps in order to reach a specific goal. So most of all the different types of problems that we face in our day-to-day lives can supposedly be categorized into one of these three types of categories. Let's talk a little bit more about problems of inducing structure. Like I said, with problems of inducing structure, the person must discover the relationship in the parts of the problem. And we actually do this on a regular basis when using our reasoning abilities. It's a very powerful problem-solving tool. The two examples over here, so analogies as well as serial completions, are just some simple problems that require you to essentially discover the relationships in the parts of the problem. So merchant is to sell, as customer is to buy. Lawyer is to client, as doctor is to patient. So to answer this these word analogies over here, you had to induce what is the relationship between this word and this word to figure out what could be a possible answer for this that would have a similar relationship with the word customer on the second pair over here. What number of letter completes each series? These are just examples of serial completion problems. So 1, 2, 8, 3, 4, 6, 5, 6, and you can probably guess the next one, which is 4. Right? To answer this question, you had to discover the relationship between every third numbers over here, and basically make an educated guess that the difference in every third number is basically -2. Similar thing over here, A, B, M, C, D, M, and the next one, and you can probably guess that, is an E. So you gotta be able to figure out again what is the underlying pattern under this serial over here. Other more complex problems that may be more relatable to you. Let's say you get into a petty argument with one of your good friends. And at the end of the argument, you both leave that argument feeling pretty dissatisfied and frustrated. And when you try to go back in your to sift through your memories about what went wrong with that conversation, you're basically trying to figure out what was there an underlying pattern to the way in which that conversation was going? Was there an indication that the conversation maybe was going south? Could you have done something to change it? Every time when you do when you are basically trying to figure out if there are any underlying relationships or patterns that is just right below the surface that explains the manifestation or the overt manifestation of your problem, that is basically a problem of inducing structure. So again, with problems of inducing structure, you must discover the relationship in the parts of the problem. Number 2, problems of arrangement. Remember I said that problems of arrangement involves arranging parts in a way that satisfy some criterion. One example over here is the string problem. So the problem over here is that there are two strings that hang from a ceiling but are too far apart to allow a person to hold one and walk to the other. And on the table are a book of matches, a screwdriver, and a few pieces of cotton. How can you tie those strings together? So if you want, you can pause this video and think about it. If not, I'm just gonna go ahead and let you know what the answer is. The answer is that you could use one of the objects that is presented over here. You could take the screwdriver over here, tie it to this string right here, and then swing that string just as though it is a string tied to a pendulum, because it now has a weight on it. When it is swinging back and forth, you can grab this or the string and then grab the string over here when it swings back at you. And so this is just one example of having to solve a problem that requires you arranging parts in a way that satisfies some type of criterion. Other type of examples that I can think of would be, say, a game of Scrabble. When you need to get the most points, you got to figure out how do you arrange the parts of your problem in a way that maximizes your amount of points. If you've ever been in an unfortunate situation where maybe you gotta travel, and you packed everything into your check-in luggages, you get to the check-in counter and discover that one of your bags are overweight. Well, now you gotta rearrange all of your stuff in your bags so that you can actually meet the constraints of the weight limitations. That might be another problem of arrangement. And there are a bunch of other examples as well, that as long as it requires you to arrange parts in a way that satisfies some criterion, that would fall under the category of problems of arrangement. FYI, in the exam, I'll probably give to you an example of a problem and then have you tell me what type of problem, which category of problem does this fall into. So be sure that you're familiar with the concept as well as various examples that illustrate the types of problems discussed here in this lecture. The third type of problem is problems of transformation. This type of problem requires you to carry out a sequence of steps of transformations in order to reach a specific goal. So the example that's described in your textbook is this. On one side of a river are 3 hobbits and 3 orcs. They have a boat on their side that is capable of carrying 2 creatures at a time across the river. Now remember that, 2 creatures. The goal is to transport all 6 creatures across to the other side of the river. At no point on either side of the river can the orcs outnumber hobbits, or the orcs would eat the outnumbered hobbits. The problem then is to find a method of transporting all 6 creatures across the river without the hobbits ever being outnumbered. So to solve this, you obviously have to carry out a sequence of steps in order to reach a specific goal. So I would encourage you, and this would be what I typically do if we had our regular class. I would get people to try to solve this problem in class as in groups. But given that this is being delivered online, I would encourage you to do this on your own. So take a piece of paper and then maybe draw a vertical line from up to down over here that separates two sides of a piece of paper, and then draw this sequence of steps. So we're starting out with 3 hobbits and 3 orcs. So you start out like this: 3 hobbits and 3 orcs on one side of the river. Remember, you gotta get all 6 across the river, and the boat can only take 2 creatures at a time. And at any step, you cannot have more orcs than hobbits on any one side of the river. So try it out. See if you can do this on your own, just for fun. And when you're done, come back again to this video. This is one way of solving that problem, and as you can see over here, this problem is tricky because it is necessarily to at least temporarily work away from the goal in order to actually solve this problem. So now you got 3 orcs, 3 hobbits on one side. You get 2 orcs to go onto the other side. 1 orc stays there, 1 comes back. This orc then picks up another orc and drops off 1 orc on the other side, and 1 orc comes back. Next, you get the orc to disembark and get 2 hobbits to get on the boat to get to the other side. Then you get 1 orc to come over as you drop off 1 hobbit. And then you drop off that orc so you can pick up another hobbit. This hobbit is doing very well over here because he is not being outnumbered. And then you drop off, basically both hobbits get off the boat, and the 1 remaining orc gets back onto the same boat again. This is kind of what we mean by, to solve this problem, you need to temporarily work away from the goal. And the orc picks up another orc, drops 1 orc back, the other one goes back again to grab the other one, and then brings back the other one, and at the end of the day we got 3 orcs and 3 hobbits. Again, to solve this, it requires you to carry out a sequence of steps or transformations in order to reach a specific goal. And this is one very good example of this type of problem. So, we've discussed the 3 types of problems. Let's discuss the common barriers that prevent effective problem solving. So, to illustrate the first type of barrier, let me show you a couple of riddles and see if you can answer them on your own. 15% of people in Topeka have unlisted telephone numbers. You select 200 names at random from the Topeka phone book. How many of these people can be expected to have unlisted phone numbers? Think about it, and once you figure it out, you can come back here. Actually, let me walk you through the other types of riddles, and you can probably see a common theme as I reveal the answers to you. So this is the first type of riddle. I'll tell you the answer in just a little bit. The second riddle is this: when Tommy was 6 years old, his sister was half his age. Now that Tommy is 30 years old, how old is his sister? Alright, think about it, write it down in a piece of paper. And let's go on to the third riddle. If a plane crashed in the border between the US and Canada at Niagara Falls, where would they bury the survivors? Think about it. Write down your answer. So in case you don't know yet, or if you just wanted to make sure, the answer to the first riddle is none. If any of these people have unlisted phone numbers, then their names would not be in the Topeka phone book in the very first place. I hope that makes sense. And the answer to the second question is his sister would be, let's see, 6, half his age, so that means his sister would be 27 years old. Some people might be tempted to say that his sister was 15 years old, simply because the word half was used over here. In the third riddle, the answer to that is, where would they bury the survivors? Drum roll, please. And the answer is I hope they would not bury the survivors, because if you survive, you should go back to your families. And so to answer this third riddle, you kind of had to ignore the leading nature of this question. Now, to answer all of these riddles, what you needed to do was that you needed to ignore irrelevant information. In these problems over here, there was irrelevant information that was being provided to you that you needed to basically ignore, because if you took that into consideration, it just made the problem even more confusing. And if you think about this in real life, for any problem that you face on a day-to-day basis, or like a weekly or monthly basis, there's really not a manual that tells you what you should pay attention to and what you should not pay attention to. And sometimes we get stuck on a particular problem, not because we're not able to come up with a solution, but because we are fixated on irrelevant aspects of the problem. That has got nothing to do with the solution. And this is one of the common barriers to problem solving. So the next time you get stuck in trying to solve a problem, ask yourself, am I paying attention, or am I being too focused on irrelevant information that is making this more difficult than it needs to be? So that's the first barrier, irrelevant information. The second barrier to problem solving can be illustrated by this riddle over here. So you've got a box of matches, over here, a box of push pins, a candle, and a wall. Pretend as though this table isn't there, because this table is not supposed to be there. I think this is drawn over here to illustrate this. You basically got a wall, a candle, a box of push pins, and a box of matches. Now your goal is to place a lighted candle on the wall such that the wax does not drip down the walls onto the floor. So how can you do that with the items that is given to you? If you want to figure this out on your own, you can pause this video and try to draw out potential solutions. Once you've done that, come back again to this video and I'm going to show you the answer. So to solve this problem, we need to push aside our tendency to perceive an item only in terms of its most common use. And this is a very definition of functional fixedness, when you tend to perceive items only in terms of its most common use. In this example, being able to see the box right here, either the box of matches or the box of push pins, as being more than just a container for the push pins or the matches, then we might be able to see its use as being a base for a lighted candle. So being able to push aside a tendency to perceive an item only in terms of its most in terms of its most common use, basically being able to go beyond functional fixedness, would be another potential barrier that you would need to address. So people who can think creatively in terms of using items in ways in which it hasn't been used before, that can give them the cutting edge over others who may be stuck in being able to only think about using things in terms of its conventional use. To illustrate the third barrier, let me give you another problem set. So using jars A, B, and C, and you can see that there are 6 different problem sets over here. So using jars A, B, and C with the capacities, let's just say this represents milliliters, with the capacities indicated in each row. So for problem 1, you got an empty jar that can take up to 14 mils, an empty jar B that can take up to 163 mils, and then empty jar C that can take up to 25 mils. Assume that there are no specific markings on the jars that can help you for example, figure out what is half of jar A or half of jar B. Assume that you can only fill up these jars to the brim, and that's the only most accurate way to use these jars. So using jars A, B, and C with the capacities indicated in each row, figure out how to measure out the desired amount of water specified here on the far right. So how can I get 99 cups of water in problem 1? And how can I get 5 cups of water in problem 2? Same thing with problem 3, 4, 5, and 6. So I encourage you to pause the video and try to do this on your own for each of these problem sets from problems 1 up through problem 6. And the reason why I encourage you to do this on your own, and the reason why there's a lot of experiential exercises here in this lecture, is because you're probably most likely to be able to understand and retain more if you do these experiential exercises as opposed to just listening to a lecture. So it's up to you. I highly encourage you to do what is probably going to be most effective for you, but ultimately you decide. So I encourage you to pause the video, solve each problem, and then come back again to this video. So it's been a while since I last did this. I believe the answer is you would need to take, let's see here, 163 minus, let me get a calculator, online calculator, let me do some quick calculations here. 163. Okay, so the answer to problem 1 is you take jar B, fill it up to the brim, so you get 163 milliliters of water, and then you take an empty jar of jar A and scoop out 14 mils from jar B. That should leave you with 163 minus 14, 149, and then now you take empty jar C and scoop out 25 milliliters of water from jar B, so minus 25, and then that should leave you with 124 milliliters. Take another empty jar of jar C and remove 25 milliliters from jar B again. That should leave you with 99. So essentially it's B minus A minus 2C, if that makes sense. It's a similar solution for problem number 2. You take 43 minus 18, that should leave you with 25. 25 minus 10, that gives you 15, minus 10 again, that gives you 5. So again, B minus A minus 2C. Similar solution with the rest of the problems, really, from problems 3 all the way to 6. Now, what you might have overlooked was that to solve the last problem, you don't need to go through a complicated set of procedures such as B minus A minus 2C. Really, all you need to do is just take 28, fill up jar A with 28 milliliters of water, and then take an empty jar C and remove 3 milliliters from 28. Now, if you were successful in overcoming your tendency to use the same strategy from problems 1 through 5 for problem 6, then you have successfully overcome your tendency to use a mental set. A mental set is what happens when people persist in using problem-solving strategies that have worked in the past. Now, there is some utility to this. Typically, the types of solutions that we used in the past has some utility. It might be worth checking out to see if it actually works. But sometimes, what comes together with that is the price of being not very efficient in being able to detect what might be the most obvious solutions to the problem that you're working with. And so that might be another potential barrier that could either slow down your problem solving process, or maybe even just prevent you from being able to solve the problem in the very first what was I going to say? Being able to solve the problem in the very first place. Alright, so far we've talked about 3 barriers so far. We have covered irrelevant information, and we talked about how that could be a barrier to problem solving. We talked about functional fixedness, being able to, or being having the tendency to get stuck on only seeing the utility of things in terms of its conventional use. Now we just covered mental set as another potential barrier. That is when we continue to persist in using problem solving strategies that have worked in the past. The fourth barrier to problem solving can be illustrated with this problem set right here. And so, what I would encourage you is to take a piece of paper again and draw these 9 dots on the piece of paper. And this is the scenario. Your goal is to draw no more than 4 straight lines that will cross through all of the 9 dots without lifting a pencil from the paper. So your goal is to draw no more than 4 straight lines that can cross through all 9 dots without lifting a pencil from the paper. If you've not done this before, then I would encourage you to do so. Or maybe you've done this before and you can't really remember how to solve this again. Either way, try it out on your own. You can pause this video, and then once you're done, you can come back again to this and I'll basically show you the answer. And this is the answer. So let me draw this out for you. So you start out, say, with this dot right here. Line 1. Line 2 goes all the way up. And we can keep going. And line 3. It's a little bit tricky to do this with a mouse pad. And then line 4. And that would be how you would solve that problem. So to solve this problem, you need to basically open up, quote unquote, open up that figure. There you go. Something which many people might be reluctant to do because sometimes we impose unnecessary constraints on the problem. Now remember, when I gave the instructions, I didn't say that you couldn't draw outside the square shape around these 9 dots over here, but people tend to, sometimes we assume that we gotta, play by the rules, or we just, again, impose unnecessary constraints on the problem that we are fixing. So that'll be another question that you can ask yourself if you find yourself being stuck in a problem. Am I imposing any unnecessary constraints on this problem set? So we've discussed 3 types of problems. There are problems of arrangement, problems of inducing structure, problems of transformation. We have discussed 4 barriers to problem solving, or 4 common barriers to problem solving. That includes paying attention to or being fixated on irrelevant information, relying on a mental set, falling prey to functional fixedness, and sometimes imposing unnecessary constraints on a particular problem. So what are some common strategies, approaches to problem solving that can help us solve a problem? Well, in general, there are 2 general approaches to problem solving. You either use trial and error or brute force, which is essentially trying out all possible solutions, like literally sequentially, and you basically discard those that don't work, that do not work. This is analogous to, if you're trying to find a link on a website. You literally click every possible link on the website to find the link that you're looking for, as opposed to maybe using a search toolbar at the top of the screen. That might be a quicker way for you to find what you need. Although using trial and error will eventually help you arrive at the solution, as you can see, it is not the most efficient way of doing it. So in the interest of efficiency, we sometimes employ what we call heuristics as problem-solving strategies. And your textbook talks about 4 heuristics that we use. Number 1, you can form sub-goals. This can sometimes help make complex problems more manageable once you break down a big goal into smaller goals that are more amenable. Searching for analogies, there'll be another way of helping you think about what might be the underlying pattern or structure that underlies your problem. You can change the representation of the problem. We'll talk about how that can sometimes help you think about a problem in a different way. And taking a break also helps, especially if you find yourself being stuck on the problem for a really long time. So let's talk about forming sub goals first. So forming sub goals allows you to solve parts of the problem one by one, thereby moving you toward success. And the usefulness or the utility of forming sub goals can be seen in this problem right here. This is sometimes called the Tower of Hanoi problem. It's a very simple version of the Tower of Hanoi problem. I've seen more complex versions, but this is enough for us to demonstrate the utility of forming sub goals. So your goal in this problem is to move all three rings right here, 1, 2, and 3, from peg A to peg C. But there are two restrictions. Number one, only the top only the top ring on a peg. So pegs A, B, and C. Only the top ring on a peg can be moved. Okay, so you can't really pick 2 over 1. You gotta move the top one in any peg that a ring may be in. Number two, a ring must never be placed above a smaller ring. So number 3 cannot be above 2, and number 2 cannot be over 1, and number 3 cannot be over 1. So those are the two restrictions. Only the top ring on a peg can be moved, and the ring must never be placed above a small ring. Now, if you think about this problem in terms of sub goals, right? Your first sub goal is to get ring number 3 to the bottom of peg C. So to do that, you gotta get rings 1 and 2 out of the way, basically. So you should move, say, ring 1 to peg C, ring 2 to peg B, ring 1 back to peg B, and then ring 3 on peg C. So now you've achieved your first sub goal, because your first sub goal is to get ring number 3 to the bottom of peg C. Now, the second sub goal may be pretty obvious to you right now. You gotta get ring number 2 onto peg C. So to do that, you move ring number 1 over to peg A, ring number 2 over to peg C. Now you've achieved your second sub goal, and you can celebrate. And the last one is to move ring 1 to peg C. Again, I can't really emphasize how this is really useful for solving big problems and helping you gain some traction. You know, sometimes you may have this really grand, say, business idea or maybe a research idea or some big proposal that you want to sell to someone. But sometimes that can be very what's the word over here? Sometimes those goals might feel like it's too big or too lofty to achieve, and one way of making those goals seem more reachable is again to break it down into smaller goals. That way, it won't be so formidable for you to take on that task. So number one, you can form sub goals. It can a lot of times help you gain traction in moving in the direction that you want to move. Now, the other heuristic that you can use to solve problems is to search for analogy. So to illustrate this heuristic, let's consider this problem. A tumor is located in the interior of a patient's body. The doctor needs to destroy the tumor with high-intensity rays. But the doctor needs to prevent the high-intensity rays from destroying healthy tissue. However, you still need the high-intensity rays in order to destroy the tumor. And let's just assume, for the sake of demonstration, that that literally is the only way, using the high-intensity rays. So how can the doctor use the high-intensity rays to destroy the tumor without destroying healthy tissue? So, I encourage you to pause the video, think about this for maybe 1 or 2 minutes, and see if you can come up with the solution. Now, most people would have difficulty solving the previous problem, but But here's another problem, and I think if I had given you this problem to solve first, you might have been able to solve the previous problem pretty easily. Um, so this is the problem right here. So a fortress is located in the center of a country. Many roads radiate out from the fortress, and all the roads have been mined so that while small groups of men can pass over the road safely, any large force will definitely detonate the mines. Now, a general wants to capture the fortress with his army, and he needs his entire army to capture the fortress, but wants to prevent the mines on the roads from destroying his army. What should the general do? Most people tend to have a better chance of being able to come up with a solution for this. See if you can think of a solution for this. You can pause the video and then come back again to this online lecture. So how can you solve this? Well, maybe you've come up with the solution of, well, if we can't get his entire army to move all at once through these roads to get to the fortress, maybe what he could do is to break his army into smaller groups of smaller groups of soldiers, and that way he will still have all of his men, and they can all still congregate in the center of the city, in the center of the fortress, while avoiding those mines that only detonate when you got any large force trying to cross over those roads simultaneously. So I hope that makes sense to you. So if that makes sense, I hope you could come up with a solution for this too. So again, a tumor is located in the interior. To destroy the tumor, you need high intensity rays. But you also want to prevent the high intensity rays from destroying the healthy tissue. So what can you do? Well, what you could do is actually do something like this. Instead of just using or focusing all of those high intensity rays simultaneously onto the tumor, you could split up those rays. So you got several small rays so that they're not big enough to destroy the surrounding healthy tissue, but when they converge in the middle, it's enough of power to be able to destroy the tumor. Now, if you think you would have been able to solve the laser problem easily if I had shown you this problem earlier, that's probably right, because you would be using an analogy to solve the problem. Analogies can be very powerful. Think about the last time you were trying to explain something very complex to someone else in a meeting. Usually using some type of concrete example helps people to think about complicated topics more clearly. And as powerful as analogies are, people often are unable to recognize that two problems are similar enough that an analogy might lead to a solution, because we tend to focus on the superficial surface features of problems as opposed to the underlying structure. But nonetheless, being able to think about other similar problems that might have a similar underlying structure may help you solve a particular problem that may be difficult to solve by itself. So think about other similar situations that may be relevant to your problem. Alright, so far we've discussed the heuristics of forming subgoals, how that can be really helpful in terms of breaking down complex problems, searching for analogies because a lot of times that helps us to think outside the box. And now let's talk about the third heuristic, which is to change the representation of the problem, because sometimes changing the way we see or represent a problem helps us to solve problems better. So this is the example over here. At sunrise, a Buddhist monk sets out to climb a tall mountain. He follows a narrow path that winds around the mountain and up the temple. He stops frequently to rest and climbs at varying speeds, arriving around sunset. After staying a few days, he begins to return to his journey. And as before, he starts out at the exact same time at sunrise. He rests often, walks at varying speeds, and arrives at the bottom of the mountain at sunset. So the challenge here is for you to prove that there must be a spot along the path that the monk will pass on both trips at precisely the same time of the day. And so when participants in a research study were presented with this problem, they were presented with this problem um, in terms of a verbal representation of the problem, a mathematical representation of the problem, or a spatial representation of the problem. The people who were presented with a spatial representation of the problem fared much better in terms of being able to prove that there must be a spot along the path that the monk will pass on both trips. So this is an example of a spatial representation or a graphic representation of the problem. So the best way to represent this is to think about the monk ascending and descending down the mountain. So y-axis is the altitude. Sunrise, let's say that starts at 6 a.m. and sunset is 6 p.m. according to the problem set. Every time he starts his journey, he starts out at the same time, but he always arrives back at the same time too. So 6 a.m. to 6 p.m. So monk starts at 6 a.m. and he walks at varying speeds up the altitude and then arrives at 6 p.m. And when he leaves the next day, he leaves at 6 a.m. and then walks all the way down, walks at varying speeds, and then arrives at 6 p.m. At some point, the monk must have crossed a point down that same pathway at the exact same time, at the exact same altitude. And all that is made possible because that monk is starting at the exact same time and arriving at the exact same time on both days. So people who were presented with, again, a graphical representation of the problem just like this one had a much better chance of being able to prove that there must be a spot along the pathway that the monk will pass on both trips at precisely the same time of the day. If you've ever taken any, say, statistics course, for instance, you will learn that there are multiple types of ways of presenting your data. You can use bar graphs, you can use line graphs, you can use pie charts, you can use box plots, all kinds of things. And sometimes changing the way in which you present the basic elements of the problem may be able to help you solve that problem better compared to one representation as opposed to others. So the next time you can't really solve a problem, try to draw out the problem or depict the problem in different ways. Talk to others to see if there could be other ways of looking at the same data that you're looking at. Now sometimes you just quote-unquote hit the wall, right? And you just cannot figure out how to solve the problem, and that happens. If you ever find yourself in that particular predicament, one way is for you to take a break. Get away from the problem, even sleep on it. There's research suggesting that participants who sleep between problem-solving exercises had a better chance of being able to solve problems after the sleep compared to those who don't sleep at all. So this is referred to as incubation, and incubation is basically when new solutions surface for a previously unsolved problem after a period of not consciously thinking about the problem. Some theorists believe that incubation effects occur because people continue to work on problems at an unconscious level after conscious efforts have been suspended. So the next time you are out of ideas, take a break, go do something else, and then come back to this same problem later on. Sometimes if you are, say you hit a barrier, say you are stuck in a mental set, right? Or maybe you are experiencing functional fixedness. Being able to take a break from that problem may help you break away from those barriers. So, a related question to problem solving is this: do the different experiences of people from a diversity of cultures lead to cross-cultural variations in problem solving? That is, do they tend to conceptualize problems, the same problems, in different ways? And the answer appears to be yes, at least to some degree. There's research suggesting that people from Eastern Asian cultures, they tend to display a more holistic cognitive style that focuses on context and the relationships among elements, whereas people from more Western cultures, so from America and Europe, tend to exhibit a more analytic cognitive style and focuses more on the objects and their properties rather than context. So, in an experiment, researchers showed animated scenes of fish and underwater objects to Japanese participants and American participants. And the participants were asked to report what they had seen in that animated scene. So it was like a open-ended type of description. And the initial comments after being analyzed in a qualitative way, the initial comments seemed different. The Japanese participants made about 70% more statements about the context or the background and twice as many about relationships between the elements here in this scene, whereas American subjects tended to report more on the fishes. And Japanese participants tended to make more comments on the background elements. These disparities in cognitive style appears to be rooted in variations in how cultures tend to think about one another, especially in a social orientation piece. Some theorists argued that the differing social orientations appear to grow out of, say, the different emphasis on individuality and independence, or the inverse of it on group and interdependence. One of the interesting observations that was made by, I can't remember which author was it, but he was talking about how car manufacturers in, say, Japan versus car manufacturers in, say, America. And he pointed out that the research and development priorities were slightly different. I mean, there were obviously similarities, but slightly different in terms of what the manufacturers were interested in. He noted that, and this was a couple of years ago, so I don't know how much this applies right now, but he noted a couple of years ago that European or American car manufacturers were putting in a lot of money into creating an autonomous car, a car that basically drives itself. And we've seen great strides in that regard, and that's pretty cool. On the other hand, Japanese car manufacturers were more interested in creating a car that is able to quite literally build a relationship with you. A car that, as soon as you step into the car, a car that recognizes your mood, is able to adjust according to your driving style, a car that is able to learn your driving patterns and where you typically go and be able to make suggestions as to routes, a car that basically works synergistically with the driver, with the human occupant, as opposed to removing the occupant altogether. And I thought that was an interesting observation that seemed to be related with this whole difference in terms of Western and Eastern cultures. The emphasis on individuality, I wonder how much of that contributed to all this research on building an autonomous car. Versus an emphasis on group and interdependence, and how that led to maybe more of a focus on developing devices that complement our functioning as opposed to replacing our functioning altogether. Alright, so we've discussed the different types of problems, barriers to prevent problem solving, approaches to problem solving, and culture and cognitive styles. Now, I want to talk a little bit more about decision making in this lecture too. So, problems are not the only kind of cognitive challenge that people grapple with on a regular basis. No, life also seems to constantly demand us making decisions, and that is what I want to talk a little bit more about today. So what is decision making? Well, decision making is essentially the act of evaluating alternatives and making choices among them. Most people try to be systematic and rational in their decision making. However, we now understand that people tend to use, for the most part, simple strategies in decision making that typically focus only on a few facets of available options that often result in quote-unquote irrational decisions that are less than optimal. So, spurred by this analysis, psychologists have devoted several decades to the study of how cognitive biases can distort people's decision making. Many decisions involve choices, essentially about preferences, which can be made using a variety of strategies. And so, in your online forum, I want you to share if to share your thoughts on these two questions here. Number one, do you think it is better to always have more choices compared to less choices? And number two, do you usually go with your intuition, or do you tend to make decisions after a conscious deliberation of evaluating all the pros and cons of your options? And if so, why? I'm curious as to what your thoughts are on that, because this relates directly to decision making. So I'll leave that to the online forum for you guys to share your thoughts on this. Now, related to decision making, we are often faced with decisions that basically requires us to judge or estimate the odds or probabilities of different events occurring. So when we're deciding what insurance to get, for example, whether that be life insurance, health insurance, dental insurance, all of these decisions involve you making probability estimates that certain events may occur in your life. It turns out that we are pretty terrible when it comes to estimating probability, primarily because we tend to rely on two heuristics, the availability heuristic and the representativeness heuristic. This slide here is all about the availability heuristic, which is basically when we estimate the probability of an event happening based on relevant instances that come to mind. So sometimes we allow our estimates, our probability, to be influenced by simply how easy it is for us to think about relevant instances. So in this example here, if you were to ask people, which is more frequent, words beginning with the letter K or words with K in the third position? Most people, especially if you don't tell them that this is a study on heuristics, most people would probably guess, words beginning with the letter K. And why is that? The reason why the first choice feels like it's the right answer as opposed to the second choice, which is actually the right answer, is because it's a lot easier for you to think about words beginning with the letter K. It's a lot harder for you to think about words with K in the third position. And if you allow your answer to be influenced by how easy it is for you to think about relevant instances, then you're relying on the availability heuristic. And sometimes that leads you to the right answer, but sometimes, like in this situation over here, that can lead you to the wrong answer. So that is the availability heuristic, when we estimate the probability based on relevant instances that come to mind. Next, representativeness heuristic. The representativeness heuristic involves basing the estimate probability of an event based on how similar it is to the typical prototype that comes to mind. So, in this question here, which is more likely? Having 6 coin tosses where you get tails every single time, or having 6 coin tosses where you got hits and 2 tails, then hits and tails, and hits again? So which of these two scenarios are more likely? The first row of coin tosses or the second row of coin tosses? Most people would probably pick the second one, right? Because it feels like this is much more likely compared to the first one. But the answer is that they are both equally likely, because the probability of an outcome for a coin toss, for every coin toss basically, is going to be independent of the previous coin toss. Coins don't have memories. They don't care about the previous outcome. They don't think, for example, oh, I've been tailed so 3 times, I guess I should be hit soon. They don't do that. Every coin toss is a 50-50 chance, and if you were to multiply all of them, for each coin toss, it's going to be the same, even though it feels like this is more likely compared to this one. So when we make a judgment like this, when we mistakenly say that this second row here is more likely, it's probably because we're basing our estimated probability based on how similar it is to the typical prototype that we have in our mind. Now, typically when you think about coin tosses, we think about how it's a random event. It's a 50-50 chance, right? And so this feels like it's more like a 50-50 chance because when you think about random coin tosses, we think about heads and tails, heads and tails, heads and tails, for the most part. Um, Even though mathematically, this is also equally likely. So, um, those are the two types of heuristics. You know, we rely on the availability heuristic. We rely on the representativeness heuristic. And the reason why we use heuristics in decision making is because, again, these heuristics help us to save time. Now, for the most part, these heuristics work pretty okay, but I guess common use or the habitual use of heuristics in decision making may likely lead you to commit some common flaws in reasoning. And these are the common pitfalls over here: ignoring the base rates, the conjunction fallacy, the gambler's fallacy, estimating the improbable, as well as loss aversion. I'm not going to talk about these common flaws in this online lecture right now. When we meet again in class, we will pick up from here. But basically, the availability and representativeness heuristics are basically the reasons why we end up engaging in these common flaws right there. So, taking a step back again, this is kind of where we're stopping in this online lecture. We've talked about the types of problems, barriers to effective problem solving, different approaches to problem solving, culture and how that can influence your cognitive style. We talked about the very nature of decision making and how we tend to use different heuristics in judging the probabilities when it comes to decision making. And then when we meet again in our next class, we'll talk about some of the common flaws that result from using these heuristics in the very first place. Other topics that we'll be covering in our next lecture involves the second part of the chapter, which is basically intelligence. So remember, cognition is more so a study about how we think. Intelligence is more so a study about how well we think. So we'll cover the rest of this chapter when we meet again. Be sure to complete the online forum pertaining to the two discussion questions that I just talked about. Remember that these online forums have points attached to them, and that you will need to not just share your own viewpoints but also comment on what your classmates say as well. So that's it. That is all the lecture for this particular segment. Let me know if you have questions, and I look forward to meeting you again in our next class.